CLion, a cross-platform IDE for C and C++. Download now.
Hey, and good morning, good afternoon, good evening, whenever you are. I want to talk for the next hour about principal misunderstandings. And we'll do a little Q&A afterwards. So, my name's Kevlin Henney. That's the easy bit. I have a bunch of socials that you can contact me and find me through. That's also fairly easy, given my name is fairly internet unique. What is not so easy and not so obvious is this word. We use this word increasingly. Principle. We talk about software development principles. And in common with most words, and something that upsets a lot of people, is that words don't have one unique definition, although they do have a lot of defaults and a lot of suggestions. So let's explore this, because people, whether they come at it from a traditional software engineering perspective or a more modern craft perspective, use this word. So let's rummage around and see what we can find in terms of its meaning. A general scientific theorem or natural law. Yeah. We don't have a lot of those in software development, okay? There's a lot of things that people would like to be that, but that's not the case. In as much as we are bound by science, we are bound by certain aspects of physics, certain aspects of mathematics, but a lot of software development is governed by the social sciences, human interaction, and a thing that we call economics. A rule or code of conduct. So sometimes the term principle has a kind of a moral suggestion to it. Sometimes it is just simply a synonym for rule. Watch out for this. We like to distinguish between the use of these idea of principle and rules. More likely, a typical one that we tend to use is this idea, again, it nods to science, but a fundamental truth or proposition serving as the foundation for belief or action. We are regarding it as almost axiomatic. Here is a thing that is true. It's not a personal preference, but here is a thing that is true. We're actually going to find that a lot of the things that people describe as principles might be better considered more at the subjective end of the spectrum than the objective end. And a fundamental assumption forming the basis of a chain of reasoning. Okay, and that's not an unreasonable, in fact, it's quite a good one. So we have a range of possibilities here. But there is a suggestion here that there's something that's fundamental or general. A principle is not something you apply as an edge case. It's not you follow a principle. The idea is you would follow a principle for 90 to 95% of the time. And there are maybe a few cases where you wouldn't. And it's not necessarily equivalent to a pattern, although it may have some overlap with that. But the idea is that a principle is relatively free of context, but gives us something that is common. And we'll actually see that there are the principles that we're going to look at either satisfy this or are rendered perhaps less credible for various reasons. So the other word in the title, principal misunderstandings, is what do we mean by misunderstanding? A failure to understand something correctly. I'm going to look at 4 key principles and also point fingers at others today. And many of the things that are in this space are based on genuine misunderstandings, either misunderstandings by the person who articulate or the people who articulate and communicate them, or misunderstandings on the part of the people who hear them. Sometimes they grow from misinterpretations. Okay, genuinely, it's just like, I got that one wrong. I saw this, and one I'm not covering today, the open-close principle, is based on these first two. The open-close principle is based on a fundamental misunderstanding about of what was originally intended by the open-close principle. Yeah. So people, I may come back to that and nod to that. The open-close principle has a point of origin and has a person of origin. Bertrand Meyer was the person of origin, and other people have pretty much misunderstood what it means and have made ceremony of it. That's going to be mostly outside the scope of what we're going to talk about today. A misconception, a misunderstanding about something, a disagreement or a quarrel. Yeah, actually, that can kind of come up every now and then, particularly when you start arguing, for example, about OCP. I have many people come to me and vigorously defend their misunderstanding of OCP. And I get it. You can be wrong. That's okay. We're all wrong at some point. But most people have not read the original sources. Why does this matter? Well, if we're regarding principles as foundational, then it does matter. If we're communicating to our colleagues, if you're a junior developer and you're hearing from a senior developer, here is a principle of development, they're telling you something quite important. And if they've misunderstood it, they're going to pass on that misunderstanding to you. But people also defend their belief. Many people I've found will defend their belief, even when they've not actually read into it. Many of our principles are passed by osmosis rather than by reading primary sources. So what I aim to do here is actually explore a little bit of that and actually find out what were the people who are advocating these various things, what were they saying or getting wrong? And why does this matter? Because I've just started off giving a bunch of definitions about words and really leaning into that. So does this stuff matter? I've had some people kind of go, oh yeah, this is just word games. You're just playing with words. It's all about it's just semantics. It's just meaning of things. It's not really important to software development. Well, this is one of those I told you so moments. It turns out that meaning matters, words matter, language matters. In fact, we've even built a whole infrastructure of AI based on the idea of language and words, which is kind of one of those big I told you so moments. It's like it does turn out that these things matter. And many misunderstandings around code already happened before the AI era. And were between people. Of course the words matter. If you don't know what the words are, how on earth are you going to develop a system based on somebody's needs? Okay, if you don't know how to communicate needs and you don't know how to articulate them, you are going to struggle. So meaning is absolutely fundamental. And therefore, misunderstanding, which is something we humans do all of the time, is something we need to both accept, but observe and adjust responsibly. Because software at some level, the style becomes a substance. It becomes real. Our choice of meanings and our choice of words and our choice of practices and the principles that we believe they support matters. So let's start off with one that is fairly common. Dry. The dry principle. Okay. And don't repeat yourself. That's what this means. Don't repeat yourself. And if we just run out onto the internet and have a look around, we'll see some fairly kind of common interpretations of this. You might be familiar with the dry principle in programming. It is indeed actually one of the more widely known ones. It encourages the reduction of code duplication, which often leads to more maintainable, efficient, and less error-prone programs. Another source, don't repeat yourself. Dry is a software development principle that encourages developers to avoid duplicating code in a system. Another source, dry is a principle of software development that aims at reducing the repetition of patterns and code duplication in favor of abstractions and avoiding redundancy. Okay, this one deviates a little bit. In other words, they're all about code. This one says that you want to avoid the repetition of patterns. Perhaps that's a little bit of a misunderstanding what the word pattern means, but that's perhaps a separate talk. But nonetheless, there is a fairly regular theme here. Dry is about reducing the duplication in your code. So where does dry come from? The dry principle was originally coined by Dave Thomas and Andy Hunt, and they did so in their book, The Pragmatic Programmer. What you see on screen at the moment is the second edition. Why am I leading with the second edition when it was actually introduced in the first edition? Because they actually have something to say. This book was published 20 years after the first edition. Okay, so this was a 2020 book. And they start off on the dry principle. When they get to that, they start off with, let's get something out of the way up front. In the first edition of this book, we did a poor job of explaining what we meant by don't repeat yourself. Okay, let's go back to the first edition. So here's my copy of the first edition. Every piece of knowledge must have a single, unambiguous, authoritative representation within a system. I don't think that's that unambiguous. I don't think they did a poor job of providing a definition, but perhaps in supporting explanation. People don't learn from abstract statements. And this is a really good one, actually. It's definitionally, it's pretty good. There's nothing I would change from a point of view of definition. But when you elaborate it through examples, that's where often the misunderstanding happens. And then people who pick up on that or anchor on a particular theme, because that's what we humans do, then that becomes the dominant narrative. The dominant narrative being that many people took it to refer to code only. They thought that dry means don't copy and paste lines of source. That is part of dry, but it's a tiny and fairly trivial part. So here's the thing. If you've got tools telling you about dry violations, they're probably not really telling you about dry violations. They're probably telling you about duplicate code violations, or rather duplication of code. It's not a violation to duplicate code. There's a little more nuance than that. It's not something we want to encourage, but there's a conversation to be had around here. Now, somebody who did understand the assignment was Steve Smith. And in 97 Things Every Programmer Should Know, a book I edited some years ago, I had people collectively contribute some of the things that they believe that programmers should know. And one of them, Steve Smith, was actually on the dry principle. And he kind of dug into this one quite deeply. And he understood what the dry principle was intended to mean and explored it from two particular key points of view, including the code duplication aspect. But there he emphasized something a little different. He highlighted a principle that is actually about removing duplicate code or consolidating, unifying it. I tend to be, when I talk about this stuff, I'm not really so keen on the idea of elimination or removal, because that doesn't tell you really the action. You're not going around just deleting it arbitrarily. The idea is you are unifying or consolidating it. That is a much more refactoring-oriented way of thinking. Anyway, he identifies the principle that people are trying to talk about, the once and only once principle. Kind of you can get what's going on with that name, which applies only to the functional behavior of code, can be thought of as a subset of dry. Oh, that's what people are talking about. So once and once only, also known as OAOO, very vowel-oriented. Where does this come from? This comes from a book called Extreme Programming Explained. XP was pretty much the approach that triggered the interest in agile development. So Kent Beck and others formulated this approach in the mid to late 90s. Kent's name's often associated with it. This is where we get things like sort of the encouragement towards pair programming, test-driven development, adopting a test-first styling in development, the more active engagement from, say, customer to the point that they are actually on site, and little ideas that seem to have passed into everyday practice, like refactoring and continuous integration. So a lot of the shifts that we see in the last quarter century can be attributed directly and indirectly to this work. Now, Kent had an idea here of simplicity. It's one of the key values of XP. And he defined what he meant by simplest from the point of view of code. Here is what I mean by simplest. 4 constraints. In priority order. And again, as with many things, there is a nuance here that many people overlooked. 1, the system, code and test together, must communicate everything you want to communicate. The system must contain no duplicate code. 1 and 2 together constitute the once and only once rule. 3, the system should have the fewest possible classes. 4, the system should have the fewest possible methods. Now, some people anchor on 3 and 4 or have a very superficial understanding of what 1 and 2 entail. They also kind of miss the idea of priority order as well. The idea is not that you're aiming for the fewest possible classes, that you are aiming for no more classes and no more methods than is necessary to communicate everything you want to communicate. So when I say communicate, notice that we're talking about concepts, ideas, types, constraints on types. Notice that Kent does not say the system must do everything you want to do. That's easy. That's just your imperative kind of coding styles. It must communicate. If you have a minimal number of classes and a minimal number of methods or functions, but it looks like just a big damn mess and you end up with really long methods, then I'm going to say that it does not communicate because you've not shown the breakdown of the ideas. If all your variables tend towards the single letter, then you have not communicated everything that you want to communicate. You've kept most of the stuff back. So the idea is communication is key. If you mean a thing, say the thing. That's a function. That's a class. Yeah, that's a header file. That's a module. That's a whatever. But that's the relationship here. Anyway, point that pragmatic Dave and pragmatic Andy were making. Dry is about duplication of knowledge, of intent. It's about expressing the same thing in two different places, possibly in two totally different ways. Do you have to change code and documentation, or a database schema and the structure that holds it, or whatever? In other words, if I have to change this, and therefore I also have to change this, yeah, say the code isn't dry. And that's the point. Most code is simply not dry, and not because of duplication in the way that people perceive it. Let's just pick on C++ for a moment. If I have things defined in the header file and I have exactly the same signatures in a corresponding source file, then that's instant violation of dry principle. Most C++ therefore violates intrinsically by design this. For the module advocates out there, that's probably exactly what they want to hear, because modules, C++ modules will avoid that. But the key point here is that this goes further than just choice of language here. It also relates to the other relationships, okay? And that might be relationships to IDL and so on. How are the generated or intentionally written pieces or parts of the code related? So let's talk about information hiding. Because information hiding is another one of those that I would like to say, I mean, I get it. I use the term loosely sometimes. When many people use it is as a synonym for data hiding. Okay, as we're going to hide the data definition. Yeah, in that case, data and information are often related. It's we often use these terms interchangeable. Formally, they're not necessarily equivalent, but there are contexts in which they are. But information versus data is actually going to turn out to be a little more important. We tend to think of data as being a bit lower level. And the idea is that data hiding here and data abstraction is its counterpart. The idea is we are abstracting. To abstract means to remove. To remove from consideration, to remove from view. And we do so in order to try and simplify something. In a large system, we need to abstract because we simply cannot understand everything that is going on. Okay, we are human and we are bounded. And we also find that this is a similar story for LLMs. They have a context window, which is of finite size. It turns out that many of the practices that are good for this, by bizarre coincidence, are good for LLMs. So, I'm always reminded of the watching a talk last year where the advice for writing code for Claude was pretty much along the lines of, hey, you should write things that are fairly abstracted, well named, fairly small, not too large, well modularized and stuff like that. It's just like, and that will help your LLM. Honestly, if you're not already doing that, now is a really good time to start, because it turns out it's been good for humans for the last, 50, 60, 70 years. Yeah. So in other words, this is a thing. So data abstraction, what is it? What do we actually mean? It's a valuable method for organizing programs to make them easier to modify and maintain. Notice this narrative is also very similar to pretty much any principle. We saw a similar kind of concept in the internet trawl for dry. But here we're actually not, I'm not doing an internet trawl. We'll come back to who's involved here. You can see in the background. We'll talk about that in a moment. Inheritance allows one implementation of a data abstraction to be related to another hierarchically. Now, the only reason I've included this here is I'm not talking about inheritance today. The only reason I'm including this here is because this comes from a paper, the addendum to the OOPSLA 1987 proceedings, Barbara Liskov, Data Abstraction and Hierarchy. This is quite an important paper because it introduces what is now these days known as the Liskov substitution principle. And it is probably the only principle of the solid principles that is actually a principle. It is also misunderstood in the context of the solid principles, but it's actually the only one that is legitimate and unambiguous in that sense. However, we're not here to talk about that. I'm here to talk about Barbara Liskov, who won the Turing Award in 2008 for her work on programming language design, programming paradigms, and distributed system work. Importantly, when we talk about this from the paradigms and programming language design point of view, her main contribution here was not insignificant. This is a paper from 1974, basically 73 to 75. She was developing a new concept, a thing called abstract data types. Okay, and this is something that has been massively influential and is not often properly attributed. In fact, there are a couple of folks who said when she got awarded the Turing Award, why is she getting an award for this? Everybody knows this. It's just like, somebody's responsible for everybody knowing them, and her name is Barbara. The stuff that she did is really, really important, particularly in language design, which I have gone into in a couple of other talks. I think there's some really interesting stuff. I'll mention a couple of things in a moment. What does she mean by this? An abstract data type defines a class of abstract object which is completely characterized by the operations available in those objects. This sounds familiar. A programmer is concerned only with the behavior which that object exhibits, but not with any details of how that behavior is achieved by means of an implementation. Oh, okay, this is a big deal. This is a big deal. And she was actually building off information hiding, which we'll come back to. But most people look at this and go, wait a minute, aren't you just talking about objects? And for those of you who know some history, you might go, well, hang on, isn't object orientation, isn't that like late 60s? Simula 67? The clue to the year is in the name. So surely this predates the period in the 70s I'm talking about. The original Simula 67, did not have the concept of hiding data. Although we assume that has always been part and parcel of the OO deal, it hasn't. Putting your procedural behavior alongside your representational data, that was the first thing. Making any of these private, that did not come along until, well, around now. And it certainly didn't visit Simula until the mid 80s, by which point it had already become kind of canon, and it was rather embarrassing that the original OO language did not support what people were beginning to perceive as a fundamental of OO. But the principle did not come from object orientation, that principle of data hiding. It is clearly in line with it, but that's not where it fully originated. So here we see in this paper, the language in question is CLU, C-L-U, short for cluster. Cluster is effectively a module. And here is what I have traced as being the first example of an abstract data type stack. I don't think there are any precursors to this, but if you find one, please let me know. Of course, stacks have been used in software since time immemorial. But as an abstract data type, I don't think it's going to precede the invention of abstract data types. So what's interesting about this is we've got a cluster, we've got a module called stack, and then we're going to have a type that we are going to create, and we're going to organize a set of operations around those types. And I've just shown a handful here. There are a couple of others. Create, which is effectively your constructor, push, pop, and top. Okay. And it's the language is very strongly influenced by kind of like Algol 60 and Algol 68. Structurally, it's got some nice syntactic touches, as well as some things that we probably do a little bit differently these days. As an aside, semicolons were optional. You could also do multiple assignment, A comma B equals C comma D. You also had the concept of iterators. If you're wondering where iterators came from, they came from Clue. And you had ideas like the yield keyword. They were effectively coroutine style. And fully integrated with high-level for loops. Just a reminder, people often think of for loops as being very low level. Certainly from a C point of view, there's a kind of like, here's your toolkit, put together a loop. But even in other languages, they've been restricted to just numeric counters, and people often think of the idea of a more structured for or for each loop or range for style as being a very modern thing. No, they're not. They are, at this point in time, over 50 years old. It's just we're really bad at picking up on the good ideas of the past. Anyway, let's take this stack class, or this stack type, and turn it into, oh, that's another point, this had generics as well. So let's turn this into a C++ template. Okay, so we've got a class template here, and I have done it in a way that is as syntactically faithful to the Clue implementation as possible, which means I'm doing explicit this qualification. I'm choosing all of my names to be the same as they were there. I've obviously got some C++ touches. So for example, resizable arrays are not an intrinsic to the language. I've gone and used vector, naturally enough there. I haven't made any changes to the implementation except those needed to make the vector work. They auto resize in Clue. If you have them as open-ended and you assign to something that isn't there, then it will, for example, pass past the end, and you assign to that, it resizes automatically. So I've adjusted it for that, but I haven't adjusted any other kind of key logic. Okay, I have also made a mild swap to, I will include const correctness, because you should always include that from the beginning. But I'm definitely not going to take this all away. I will do a little bit of tidying up here. Next bit of tidying up is, the constructor. I'm just going to make that defaulted. That's absolutely fine. I'll get rid of all of this qualification. And the next tidy up is I'm actually going to make it a little more idiomatic while staying within the constraints originally indicated. So I am going to use move semantics. I don't need to have a separate value tracking the size of the thing. And, I'll leave it very much where it is, that as being a fairly faithful re-implementation. But here, notice I was able to do all of that. This has the same behavior as this, has the same behavior as this. Okay, and when I talk about behavior, I'm talking about semantics. So therefore, the public interface is stable. The private implementation, how I have used that, has changed. This is data hiding. So when I said that this was building off a number of ideas, and when I said that these ideas did not come from object orientation, where did they come from? This kind of data privacy idea. The paper normally cited in this context is David Parnas's On the Criteria to be Used in Decomposing Systems into Modules, which is 1972. And he talks about this. He says, the decomposition was made using information hiding as a criterion. Every module, so he works through an example and explores that, and then he talks about how that example differs from, say, analyzing your control flow and initialization sequences and stuff like that, modularizing around time when things happen, or order in which things happen. In other words, having a big module called init or something like that. So every module is characterized by its knowledge of a design decision which it hides from all others. Its interface or definition chosen to reveal as little as possible about its inner workings. Interesting about interface or definition. He's actually saying that you might have a textual definition of this. That actually turns out to be slightly important. But this is not the paper that introduced information hiding. People often think it is. That paper is 1971. Ignore the 1972 at the top. Right, corner. This paper was actually published in 71. Information distribution aspects of design methodology. Some properties of programmers are discussed. Of programmers? We're not talking about the code, we're talking about the people. System documentation, which makes all information accessible to anyone working on the project, is discussed. Oh, this is about documentation. This ties back to the definitional aspect. I was kind of definitional wording I wanted to hint at. The thesis is that such information broadcasting is harmful. In other words, the idea of writing everything down so that everyone can know it is harmful. That it is helpful if most information can be hidden from most programmers is supported. That's really interesting. Because that's not what people mean by information hiding. But that's what Parnas, who introduced the idea, meant by it. We're not going to tell you how this is built. That's what he's saying. We can avoid many of the problems discussed here by rejecting the notion that design information should be accessible to everyone. Instead, we should allow the designers, those who specify the structure, to control the distribution of design information as it is developed, hence the title. Okay, this is kind of probably not what you were expecting. This is what information hiding is. Of course, it includes the things we call data hiding, because that's part of it. That's, in other words, if I make sure that you can't take advantage of that in source code by making it private, then that supports information hiding. But information hiding is a much bigger idea than just data hiding. It's actually, I'm not going to make that available to you. You can see that this doesn't sit well with the idea of knowledge transparency and open source, and this idea that we should honestly just not be controlling or treating developers like idiots. Now, I'm not saying that you have to know this, and I do recognize that there are cases from a corporate point of view where holding back implementation decisions makes certain sense. There is the idea that, if we tell everybody how everything's implemented, then they can find their way in and hack it. But we also see the open source philosophy that basically says, like, yeah, we have nothing to hide. And in fact, if people can see what we're doing, they may be able to spot problems themselves. The information hiding is the very antithesis of open source. We can avoid conflict by designing the external interface but hiding the details that we think likely to change from those who should not use them. Now, he doesn't mean this with any kind of malice, but he is talking about the idea of, and I sympathize, because sometimes if you give people pieces of information and they don't know what to do with them, they will still use that piece of information. They'll just misuse it. They will misapply it. They won't be able to, when you're unfamiliar with something, you won't be able to weight the relative pieces of information. You'll overwhelm people. I'd rather just tell you, hey, here's this API. Here's the behavior and how it works. And I'm not doing it because I'm being malicious. I'm probably doing it because, honestly, I don't know how I want to implement it. Or I would like the freedom to be able to change how I implement it. Or it's a trade secret. Or I want to make your life simple. So I'm not going to give you everything. I'm going to give you the things that you need. And a lot of people go like, yeah, that's absolutely fine. But notice that it is not just down to this simple idea of information as data. Now, what do we mean when we start talking about, let's look at this point of view. Designing the external interface, but hiding the details that we think are likely to change. Now, that sounds really good. And when we talk about hiding, that's not saying you can never look, because obviously, as you're very familiar, I can immediately open up. I sometimes joke that there's that things like, yeah, look, this is private, and it's like, well, it's not private because I can see it on the screen. Okay, it's private from other code, but it's not private to the reader. So in that sense, we will say that private sections in C++ do not support information hiding, although they support data hiding, because I can just open up the file and there it is. And I can, if I got all my definition in the header, I'm just looking at that going like, yeah, I can see everything that you're doing. There's no information hiding there. There's still data hiding, but there's no information hiding. But this does, whichever way we look at it, there is this idea of like, we would like to talk about the external interface. Here's the external interface. It's the bit that is public. But it's not just the syntax, it's the semantics. Okay? There is a lifecycle model of behavior here. We can describe the behavior structurally. Okay? A new stack is empty. An empty stack has no top. Okay, a non-empty stack, it retains a push value as its top. A non-empty stack on popping returns previous push and reveals previous top. We've got all of this. And in fact, we can turn this into a set of tests. So these are actually literally the catch two tests that I used to check that code refactoring I showed you earlier. Okay, that's the definition of the interface. The interface is not just the syntactic construct; it is all the semantics and the relationships and concepts and tests that go into that. So here's the point. This is what we mean when we talk about the interface definition. We go to a 1983 paper by Butler Lamson, Hints for Computer System Design. He says an interface is a contract. That's what it is. To the best of my knowledge, this is the earliest use of the term contract and the contract metaphor in software development. It predates the use by Bertrand Meyer by a few years. And that's program by contract, which has led to the contract model in C++, which has been ongoing in C++ for approximately 2 decades. Looks like it might actually arrive. And the problem is that the notion of contract embodied in the C++ contract is a tiny sliver of a contract. Tiny. Borders on useless. Yeah, I said it. But not necessarily totally useless, but people might want a little bit more reality check before they think of it as the final solution to their semantics and their specification problems. An interface is a contract to deliver a certain amount of service. That is the full kind of concept there. Now, I've got to talk about the solid principles because those are the ones that people often associate with. And honestly, they're not really principles, most of them. I hinted earlier that there are problems. The open-close principle is wrong in so many ways. It's difficult I could dedicate a whole talk to it, which is why I'm not going to cover it today. Lisk-off is actually the most sound principle in there. It is robust, but it is also misunderstood and it's miscommunicated. The one I'm going to focus on today, and then you've got interface segregation, which is basically just a footnote to SRP, and you've got dependency inversion, which is almost gets to being a good principle. The name betrays it and undermines it a little bit, but it's a reasonable pattern, but I wouldn't necessarily call it a principle. However, we are going to focus just on one, the SRP, single responsibility principle. Okay. Now, when you hear that, the thing is that words have a particular suggestion and words matter. If I hear single responsibility principle, a number of things come to mind. Single, one. Responsibility, that something is obligated to do something. Okay, it has a duty to do something. Principle, you should be applying this pretty much everywhere. Okay, it's a high-level suggestive wording. This is not unreasonable. It actually chimes very much with something that we may already be familiar with. What you're seeing on screen is an extract from a book by Peter Sallis, A Quarter of a Century of Unix. So this was written in the 1990s. And he kind of quotes something that Doug McElroy said. Doug McElroy didn't say this necessarily fully back at the time, but it was a case of, this is the Unix philosophy. What was he talking about? Write programs that do one thing and do it well. Okay, there's a bit more to that quote, but that's not the bit that we care about. It sounds like SRP is a repetition of this. But we find that actually it's not quite that simple. And although suggestively the name is not unreasonable, the problem is that responsibility is not a computer science concept, and we're going to have to, a duty to do something. It does feel like that's going to be doing an awful lot of work when we try and push it to do some work. Here's the thing, though. It's not about responsibilities. It's single reason for change. Reason for change. Yeah. So, this was coined by Robert Martin. And we can find it described in his Clean Code book and some of his other works. The single responsibility principle states that a class or module should have one and only one reason to change. It's like, whoa, wait a minute, you just did a kind of bait and switch. You used the word responsibility, but now you're just talking about reason to change. Okay, well, Let's go with that because I already have an idea of what change is. Well, if you're in software, you've got to have some idea of what change means. I've already got a good idea of what change means and a reason for change. Why might something change? Okay, we've already done stacks. Let's switch to queues. Okay, so I can pop something from a queue, or I can pull something from a queue, or I can dequeue something from a queue. Right. Okay. So the point here is in defining an interface, I'm defining a protocol, and there are a number of places where this language set might come from. I might be participating in an existing framework or net set of naming conventions. In other words, I would say, right, I'm participating in that, and that might give me this, or it might give me this, or it might give me this. Versus participating in another domain's naming approach. So one reason for change would be because you change the conventions that you are adopting. You change the context in which you are executing something, and therefore the conventions that you follow, the protocol that leads you. So in other words, interface change at the level of the semantics of the name choice. Okay. And as reflection starts becoming a thing, that becomes really important. For those of you who work with languages other than C++, you'll already recognize that naming has deeper architectural implications, okay? Because in some cases, a naming convention is indicative of participation in a framework. It's like it's like saying this must inherit from that in order to participate in this activity or in this framework's activities. Okay, so that's one reason for change. But we also have another reason for change. Another reason for change is what happens when we try and dequeue from an empty queue. When it's depleted, what happens? Well, one way I could do this is that I could choose to say that this is an error case. And I could signal that with exceptions. Okay, I could use the standard exceptions, or I might have a different set. So one reason for change is the choice of, am I going to, is the way in which I indicate this is an error. But I might also choose for it not to be an error. So I might just say, yeah, it's perfectly acceptable. And typically with queues, yeah, it's perfectly acceptable for this to be empty. It's not an unreasonable case, and it's not unreasonable to ask it. Why is it queues and stacks, although we like to think of them to be very similar, they're not. Their context of use is typically very, very different. And we might say with a stack, it's a matter of correctness. With a queue, no, actually, there are genuine issues here, perhaps concurrency. We'll come back to that later. But it's genuinely okay to have an empty queue and to try and dequeue from it. That's acceptable. We're just going to say, yeah, there was nothing here. We're not going to set the value. Or we can embrace a little bit more C++ 17-ishness and say, we will always give you a return, but that return will be either there was something or there wasn't something. Or we could choose to decide it is an error, but I'm not going to use exceptions. I'm going to use an expected approach and replace optional with that. And basically, so I've got the T, but I've also got the alternative is the error. So that's another reason for change. And then I can also change the internal representation. I might choose to use a list, okay, standard W-linked list from the STL, or I can use a deck. Okay, so these are perfectly acceptable, and we've already talked about that under the heading of information hiding. And this is perfectly acceptable data hiding. So another reason for change. Okay, so a class contains the reason for change. Also the execution environment. We might have a queue in a single-threaded environment, but I might also have a queue in a multi-threaded environment, and I might wish to use my queue for actual inter-thread communication, and therefore requires safety, a transactional safety that is governed through critical sections and explicit locking. Yeah, I've lost count of the number of reasons for change I've now got. But that was a pretty small class, and we've already kind of hit a number of things. So yeah, I'm going to go with the idea that reason for change is a fairly is not at its surface value. You're going to need to redefine what you mean by reason for change. I mean, you've already redefined the word responsibility, and it feels like there's a little bit of a problem here. Okay, the principle gives us both a definition of responsibility and a guideline for class size. Wait a minute. The principle gives us a definition of responsibility. That you keep using that word. I do not think it means what you think it means. So the real problem we have is that, I mean, we know that naming is hard. And actually, if you look at much of the published stuff by Robert Martin on SRP, he has to spend his time explaining what should be a really simple principle by redefining the words that he uses and qualifying it just so he can keep the name. It's essentially the principle is flawed and it's wrong. It misuses English. It misuses computer science. But we do use the term responsibility. The term responsibility in terms of software has been used. It's not a crisp computer science kind of concept, but we do use the terminology. The terminology has existed in terms of naming an approach, responsibility-driven development by Rebecca Worst-Brock in the late 1980s. It's a very good example of that. But the term within OO circles has been used. And this is going to be where Robert Martin picked up the use of the term, because certainly where I picked this stuff up in the 90s. So let's have a look. Mid-90s. This book by Grady Booch, 1996. It builds on his earlier object-oriented analysis and design books, which published when was it? 1991. Second edition was 1994. And the thing about Grady is he's really good at definitions. So he actually goes and defines, and it's not just he's good at definitions, he does actually put some effort into them. Responsibility. Some behavior for which an object is held accountable. Okay. Yes, that actually works very well from the point of view of English. Okay. But keep in mind the word responsible has been in English for over 400 years and responsibility has been in English for over 250. You can't go around saying, by the way, a single responsibility principle, I'm using the word responsibility, but it doesn't mean what you think it means. I'm using it to mean something different. I'm calling it reason for change. But also, by the way, when I say reason for change, it's not what you think of as reason for change. I'm going to have to be really carefully crafting it to make sure that all of the other reasons for change are not included in what I mean by reason for change. Honestly, I know software development is hard, words are difficult, but at some point you've just got to say, hang on, stop. Let's read the original sources. What's really going on here? A responsibility denotes the obligation of an object to provide a certain behavior. Let's go back to the queue. Right. Okay. So we've got the queue. It's bounded. Okay. In practical environments, you don't really want unbounded queues. You want a bounded queue. Okay. So I think this is a behavior. I'm not happy to be vague about this one, but the idea that I should be able to create something with its boundedness. Cool. I should be able to ask it whether or not it's empty. It doesn't feel like a behavior. You know, it's not really doing anything. There's not a responsibility here. Or I should be able to check whether it's full. Although you could equally well argue, yeah, there is a responsibility to allow the user to understand the the limits and the boundedness of this. So this is a maybe. And then in queuing, that to me feels very much clear behavior, and dequeuing feels very much clear behavior. Okay, so I'm kind of happy with that. So depending on how you want to count that is somewhere between 2 and 4 responsibilities. He also adds an occasion the delegation of that behavior to some other object. The previous definition he already established by the early 90s. What do we mean by that? Delegation to another object. For example, I might choose to have notification when I've tried an activity that cannot be properly fulfilled in the way that we expect it. Okay, so if I try and enqueue on a full thing, I'm going to get false back from it, but I might also want a callback. Maybe I'm going to use that callback for logging, or maybe at a side actually I'm going to throw an exception on it. But whenever I plug in, the idea is my delegated object in this case is just a humble function object. So we've got that idea. Now, what really boosted the use of the word responsibility in software development was the idea of the CRC card. Okay, now this was from Ken Beck and Ward Cunningham, a laboratory for teaching object-oriented thinking. This is a late 80s thing. This really is what planted in many people's minds the idea of responsibilities being significant as a way of talking about objects. We introduce CRC cards, which characterize objects by class name, responsibilities, and collaborators. Okay, CRC. Here's an interesting thing. Notice it's plural. Responsibilities. It's not characterized by class name, responsibility, and collaborator or collaborators. Responsibility. Responsibilities identify problems to be solved. Yeah, your classes typically solve more than one problem. They have to address more than one issue. There's normally something that they play a role. They're often a role between two different things. In fact, the queue is a really good example. A role, a queue is used between a producer and a consumer. It has a responsibility to each of them. Okay, it plays two different roles. From one, it plays the point of view of a supplier, and to the other, it is one is a sink, the other is a source. And some people might go, oh, no, you've used the word and. Oh, that's a really bad thing. You know what? Sometimes it is, sometimes it isn't. But the idea here is that responsibilities is the normal thing. Responsibility serves as a handle for discussing potential solutions. Look through your classes, look through your code. Recognize that many of the things that you have there are structural elements that join two things or two or more things. They're responsible for more than just one thing. Okay, there is this idea of the oneness that people have become a little bit entrapped with. Now, I'm not just about to tell you that putting and in a name is a good thing. It isn't. It's generally a smell. But the idea is that naming and responsibilities are not always identical things. They are not isomorphic. The principle gives us a guideline for class size. Yeah, and that's not a good thing. Because if you follow the letter of this law, and it kind of is presented that way, it is kind of a bit problematic. So, Robert Martin contributed to 97 Things Every Programmer Should Know, and one of the things he contributed was single responsibility principle. And I included this, by the way, as a point. I include lots of things that I don't 100% agree with because I think it's important for people to hear these points of view. There are pieces in that collection of 97 things that contradict each other. And I had somebody tell me that was confusing for them. And it's just like, well, no, you're being invited to think. I'm not saying there's one true way of doing stuff. But nonetheless, this is a well-written little piece. I disagree with it a bit. But I want to focus on one aspect. One of the things is that Robert Martin does advocate that SRP is not simply about an object-oriented principle. Some people assume it's just an object-oriented principle. Even back in the clean code days, he was saying, oh, module or that. But here, he pushes it a bit further. A subsystem, module, class, or even a function should not have more than one reason to change. Okay, well, let's just take that for a moment and just see what that leads us to. Because if we've got a subsystem, let's just use the structuring that he's given us. A subsystem can logically contain one or more modules. And that may be a C++ module or some other kind of module. Okay, but a subsystem is going to be a collection of things that are larger. Yeah, if you're thinking Python, you might be thinking, hey, it's a folder or indeed a package, and this contains modules. A module can contain one or more classes. Okay, if I'm just thinking like conventional C++, then I might be thinking, hey, a subsystem, that's a directory. My modules are going to correspond to my CPP files, and a CPP file can contain one or more classes. Now, often I like to have a one-to-one relationship, but that's not exclusive, and nesting also allows us to have more than that. And then we're going to have one or more functions. Now, if you apply SRP strictly as reason for change and all the rest of it, then you do end up with a class size indication. The only way to do this is where you have one. Because if I can change, if a subsystem has only one reason to change, and my module has, and I have, two modules, each of those has a reason to change. So that now means my subsystem has two reasons to change because it contains two modules. You see where this is going. And indeed, you do end up with this crazy fragmentation. If you actually run really strict, so most people do not understand SRP. They just think of it as being just a general cohesion thing. And if you actually follow what the advice of SRP, and its bizarre constraints on what we mean by reason for change, you end up with lots of classes that have one function. In other words, you end up with fragmentation. You don't end up with a coherent set of code. You end up with a bunch of functions scattered all over the place. And that's hard to comprehend. We find it hard to comprehend when everything is all in one place. We also find it hard to comprehend when everything is scattered around. The skill in design is trying to find that. In fact, Grady Booch highlights this. The distribution of responsibilities is a critical decision. Okay? It is wrong to have too few classes causing each other to do too much. In other words, that's where you have a clumping. That's where you have your blob classes and it's just all in one place and it's too much to think of. Just as it's equally wrong to have too many classes where each does too little. In other words, if you've got a class that has only a single responsibility that leads to a single method, that's too little. In fact, every class should embody only about 3 to 5 distinct responsibilities. So we have this thing here. The point there is that we dig through the history. The term was introduced by Robert C. Martin. Yeah, this one's recorded quite well on Wikipedia. Martin described it as being based on the principle of cohesion, as described by Tom DeMarco in his book Structured Analysis and System Specification, and Myla Page Jones in the Practical Guide to Structured System Design. Now, I happen to have the first book. Beautiful example of 1970s publication. Mid-1970s, I'm trying to think, 75, 76, thereabouts, or thenabouts. What we really want is meaningful principles. SRP is not a meaningful one. Let's go, rather than basing something badly on something, what's the original say? There are, by the way, this is not the only original. There's a bunch of stuff in the 70s that was can all claim to be in this space. Cohesion is a measure of the strength of association of the elements inside a module. A highly cohesive module is a collection of statements and data items that should be treated as a whole because they are so closely related. Any attempt to divide them up would only result in increased coupling and decreased readability. The idea is you're binding many things together. They naturally go together for a variety of reasons that we've already actually highlighted. But the idea of the single responsibility principle, many people misunderstand it to be cohesion, but it's not. If you want a principle, tell your colleagues to stop using solid and start using real stuff. Yeah? High cohesion is what you want. And that's not about number counting certain things. It's not about counting the number of times and occurs in certain things. When you actually understand what was originally being said and has been repeated, clarified by Rob Munt of the SRP approach, it's actually not a very good approach and it's going to lead to fragmentation, which is cognitively misaligned with the way that we like to reason about code. So one of the things we do want to do, we're going to end on separation of concerns. Another principle. Let us look to the wisdom of the web. It's a fundamental principle in software engineering and design, aimed at breaking down complex systems into smaller, more manageable parts. The goal is to organize a system's components in a way that each part addresses a single concern or a cohesive aspect of functionality rather than mixing multiple concerns together. Okay, so this is an unmuddling thing. That sounds good. Yeah. Cohesion is bringing things together. The idea is that we don't want to bring everything all into one place. We need to separate things. That feels reasonable. And so this is very structural. The goal is to organize a system's components. Right. Then we have this one, separation of concerns, also known as aspect-oriented programming. That won't surprise me. No, it isn't. They are related, but they are not synonyms. Is a design principle, that's the word we're after, for separating programming into distinctive sections so that each section addresses a specific concern. Okay, a structural aspect here. Again, and to the wisdom of Gemini, such as it is a design principle that organizes a software application into distinct independent sections, each handling a separate aspect of the program's functionality. Okay, right. Okay. So this approach simplifies development, improves maintainability, or we've heard this narrative before, and enhances flexibility by reducing code overlap and making it easy to test and modify individual components without affecting others. In other words, this is a structural approach. Separation of concerns is about separating things structure. It is about decoupling and therefore invites us to talk about coupling. So let's pick up the narrative from the Tom DeMarco book. Coupling is a measure of the interdependence of modules. The higher the coupling, the more likely it is that changes to the inside of one module will affect the proper functioning of another module. Okay. But if these two things are tightly coupled and I change this, and that always causes ripple effects, either build effects, but more significantly breakage, semantic breakage, or even actually syntactic breakage. But the idea is you don't want everything coupling, you don't want everything depending on everything else. You want loose coupling. Obviously, coupling is something we would like to minimize. Coupling also has a strong effect on the readability of both the design and the code of each module. If coupling is minimized, you can read through a given module without having to look inside any other module in order to complete your understanding. Now, notice how sympathetic this is with all the things that we have said are kind of good things. But also this actually does reinforce some of what Parnas was trying to suggest with information hiding, although we're not being quite as brutal and strict about it. But the idea is a needs basis. I'm working on this code. I shouldn't have to understand. I should not be forced to understand the interior of something else when I'm merely a client of it. Okay. I want to rely on its contract. Okay. And again, reminder, contracts, not just pre and post conditions. I think we're about to enter an era with C++ developers where we're going to have to go around telling people, no, that's not really the contract. That's just your pre and post conditions. Yes, we do understand that's how the word has been used. But no, there's more to it than that. Nonetheless, I'll leave that for future talks. The data is all declared right there, either as private data or as pass parameters. Notice the private stuff. It kind of already started creeping in here as being a thing that was normal. It's mid-70s. Right, so all this sounds really good. It sounds like we've got a case for separation of concerns. There's nothing been misunderstood, except go and read the original source. Now, a meta point here, you might be saying, wait a minute, are you telling me that, Kevlin, that every time I start using a principle and telling my junior developers what we need to follow this principle, that principle, I need to go and read the original sources, or at least something that is fairly a secondary source that is very well informed? Because that sounds like a lot of work. I'm saying yes. And yes. Knowledge has friction. Okay. Misquoting other people, no matter what your intent, we all do it. So this is not a moral attitude. But we all make mistakes. I've made mistakes with some of these principles in the past. I've given things benefit of the doubt and then realized actually when I read the original, there was a very different story going on. And that's insightful and inspiring, can teach you more than you thought you knew. Separation of concerns. Where does it come from? It comes from Edgar Dijkstra. On the Role of Scientific Thought. This is a 1974 paper. He'd already used the term separation of tasks being significant in late 60s and early 70s. But here he specifically lays out this idea of separation of concerns. Okay, so we know that a program must be correct. Well, we would like it to be, okay? But he's big on correctness. So correctness is an aspect that he cares about. It's a concern. We can study it from that viewpoint only. We also know that it should be efficient, and we can study its efficiency on another day, so to speak. What he's saying is that these are concerns. And he's saying, but nothing is gained, on the contrary, by tackling these various aspects simultaneously. I think that's a little bit blunt and a little bit black and white, so I'm not entirely sure is where we want to go, but he also acknowledges this. It is what I sometimes have called the separation of concerns, which, even if it's not perfectly possible, no, it is. We're humans. We bring things together. And actually, sometimes it's important to bring things together, as he also describes in his writings, is yet the only available technique for effective ordering of one's thoughts that I know of. What's he really talking about here? This is what I mean by focusing one's attention on some aspect. Don't confuse that with aspect-oriented programming. This is effectively what separation of concerns is. It's an attention management technique. It does not mean ignoring the other aspects. It is just doing justice to the fact from this aspect's point of view, the other is relevant. It is being one and multiple track minded simultaneously. I think there is something here, although I consider it as a practice to employ, but you've probably been in those situations where people have been, you've got one person in the corner banging on about performance, and then there's somebody else banging on about the tests for the functionality, and and everybody's trying to do all of these things, and you're being pulled in multiple directions simultaneously. And perhaps sometimes you just need to start somewhere. In other words, let's just build a thing that is functionally satisfactory, And then we will discuss its performance rather than overthinking every single aspect simultaneously. Because if the thing that I build is not satisfactory for performance, then you know what I'm going to do? I'm going to write another thing. Hey, genius idea. Putting the soft into software. What a great concept. If the thing is not fast enough, throw it away. But Kevin, didn't we just waste our time? No, we waste our time by trying to solve all the problems simultaneously. We didn't waste our time because now we know what it's supposed to do. And now we know something about its performance. Up until the point you created it, you didn't have any kind of benchmark. You just had ideas in your head. This is the territory for micro-optimizations, and time wasted on that. Really, all he's talking about is separation of concerns is a way of focusing on one idea. You know, oh, we value all of these things. Yeah, in a real software system, you're going to value so many different things. You can't do justice to them all simultaneously. Focus on them and then start finding out where there's friction between them. Find out where there's sympathy. Oh, that's really cool. This is a really simple approach and it's really fast. Wonderful. Now you bring that concern back in. But don't try and muddle yourself. What about security? This is enough. What about, you can do lots of what abouts and never get anywhere because you are overwhelmed. So let's talk about this. These are structural things. Separation of concerns is an attentional thing. And of course, separating out elements of structure, reducing coupling between things does allow you separation of concerns, but for functional structural units, all of these other aspects, maintenance, exceptions, testing, threading, performance, security, they're also part of the separation of concerns. They don't end up in separate modules. People have misunderstood separation of concerns to be just decoupling, structural decoupling. It's not. That's a subset. So, quote my friend Russ, principles matter, but most of what we defend so ferociously are not principles. They're preferences dressed up in moral costume. Thank you very much.